How many people would you need in a hypothetical room to be pretty sure that you would get a match between their birthdays? Let's say a 50% match, for example. Would you need 100 people? 200 people? Maybe 300 people? Well, if you guessed anywhere in these numbers, you're totally wrong. In fact, you only need 23 people to be 50% sure that you'd get a birthday match. 23 seems like an absurdly low number compared to 365, the amount of days in a year. Shouldn't there be a greater number of people to be 50% sure? Well, actually no, and here's how it works. Let me explain the math behind this. First, imagine 3 people in a room. Let's figure out how many different ways we can draw connections between these people. Since a connection is between 2 people, 3 choose 2 will get us the amount of connections. We're essentially figuring out the amount of combinations between 3 people in pairs of 2. This is the choose formula. N factorial divided by k factorial times n minus k factorial. Imagine n as 3 and k as 2. How do we get this formula? Here's an intuitive proof. Let's take a different example. 4 people in 2 slots. The people are the yellow circles and the slots are the lines. On the first slot, we have 4 people we can choose from. And on the second slot, we only have 3 because one of them is already chosen on the 4. Okay, well, we get 4 factorial divided by 4 minus 2 factorial. Where did that 4 minus 2 factorial come from? Well, that's just to cancel out that 2 times 1 at the end. And because we don't want how many ways can you arrange 4 people into 4 slots. That's going to be 4 times 3 times 2 times 1. But we don't want that 2 times 1 right now. We just want 4 times 3. And 4 minus 2 will get us 2. And 2 factorial is going to just get rid of that in the numerator and denominator because they'll cancel out, which leaves us with 4 factorial divided by 2 factorial because 4 minus 2 is 2. Well, that's not enough though, because AB is going to be counted as the same as BA, but AB is obviously BA. We're looking for the number of combinations, not permutations. Permutations will count BA and AB as different things, but combinations will count them as the same, and we want combinations currently because a pair doesn't matter which order it is in. Okay, so how many ways can you arrange 2 people into 2 slots? Well, there are only 2 ways, because that's 2 factorial. Well, to get rid of that, all that extra people from the BA type, we can just divide by 2 factorial equals 2, so we get 4 factorial divided by 4 minus 2 factorial times k factorial, which currently is 2, and that's how we get the combinations formula. Okay. So applying it with 3, we get 3 factorial divided by 3 minus 2 factorial times 2 factorial equals 6 divided by 1 factorial times 2 equals 3. Okay, now let's think about it with 23. Choose 2. It turns out there are 253 ways to do it. Instead of calculating the probability that a pair share a birthday, let's calculate the probability that they don't. It's much easier. Well, the probability that a pair sharing a birthday is only 364 out of 365. It's pretty bad odds, but with 253 combinations, we need to make sure that every single one of these pairs don't share a match. So we need to multiply 364 over 365 253 times to find the probability, and 364 over 365 raised to the power of 253 turns out to be 0.4995. So this is basically approximately 1/2. Remember, this is the probability that they don't share a birthday. Subtract 0.499 from 1, and you get something a little bit over half. So it's more than likely that with just 23 people, at least 2 of them will share a birthday. Pretty interesting, isn't it? Okay, you probably understood the proof for this, but imagine a scenario with 70 people. In fact, if you do the same method I used before, you will get approximately a 99.9% chance that they share a birthday, even though 70 is nowhere near as 365. Later I'll show a more intuitive proof using a little bit of programming. Here's the second part to the birthday problem. Here I've created a simple C# script which basically allows you to enter in a certain number of people that you want to generate. It's going to generate the amount of people, and then it's gonna assign each person a birthday. After that, we're gonna loop through all of the birthdays and see if there are any matches. Let's test this out. Sadly, you can't see the window I'm gonna be running it on because the screen recorder only records one window at a time. I'm just gonna go with 23, and that's what I'm entering right now, but you can't see it. And right now I got unlucky and I got 0 matches. But this time I'm gonna try again. And instead of 23, perhaps we can try 30. Still I got unlucky and had 0 birthday matches. What a higher number, 50 perhaps? Oh wow, I got 3 birthday matches. Just with 50 people, just take time to consider that we only get 3 pairs of people that have a match. Isn't that pretty cool? Because 50 is not a very large number compared to the number of possible birthdays. It's all about the combinations, not the amount of people. And if you want to go really crazy, you can try a big number like 100 or 1,000 perhaps. And with 1,000, I seem to be getting a lot of matches. Okay, there, it loaded. 1,391 birthday matches. And finally, let me test out 365. Remember, 365 is the amount of birthdays possible. Let's see how many matches you can actually get from that much. Oh, 188. That's actually pretty high. Higher than I expected. That's it for now.